Binding energy is the energy required to disassemble a whole system into separate parts. A bound system typically has a lower potential energy than the sum of its constituent parts. This is what keeps the system together. Often this means that energy is released upon the creation of a bound state. This definition corresponds to a positive binding energy. General idea. In general, binding energy represents the mechanical work that must be done against the forces which hold an object together. Disassembling the object into component parts separated by sufficient distance that further separation requires negligible additional work. At the atomic level, the atomic binding energy of the atom derives from electromagnetic interaction and is the energy required to disassemble an atom into free electrons in a nucleus. Electron binding energy is a measure of the energy required to free electrons from their atomic orbits. This is more commonly known as ionization energy. At the molecular level, bond energy and bond dissociation energy are measures of the binding energy between the atoms in a chemical bond. At the nuclear level, binding energy is also equal to the energy liberated when a nucleus is created from other nucleons or nuclei. This nuclear binding energy is derived from the nuclear force and is the energy required to disassemble a nucleus into the same number of free, unbound neutrons and protons it is composed of, so that the nucleons are far distant enough from each other so that the nuclear force can no longer cause the particles to interact. Mass excess is a related concept which compares the mass number of a nucleus with its true measured mass. In astrophysics, the gravitational binding energy of a celestial body is the energy required to expand the material to infinity. In bound systems, if the binding energy is removed from the system, it must be subtracted from the mass of the unbound system, simply because this energy has mass. Thus, if energy is removed from the system at the time it is bound, the loss of energy from the system will also result in the loss of the mass of the energy from the system. System mass is not conserved in this process because the system is open during the binding process. Mass-energy relation. Classically, a bound system is at a lower energy level than its unbound constituents, and its mass must be less than the total mass of its unbound constituents. For systems with low binding energies, this lost mass after binding may be fractionally small. For systems with high binding energies, however, the missing mass may be an easily measurable fraction. This missing mass may be lost during the process of binding as energy in the form of heat or light, with the removed energy corresponding to removed mass through Einstein's equation E equals mc2. Note that in the process of binding, the constituents of the system might enter higher energy states of the nucleus, atom, molecule. But these types of energy also have mass, and it is necessary that they be removed from the system before its mass may decrease. Once the system cools to normal temperatures and returns to ground states in terms of energy levels, there is less mass remaining in the system than there was when it first combined and was at high energy. In that case, the removed heat represents exactly the mass deficit, and the heat itself retains the mass which was lost. This mass appears in any other system which absorbs the heat and gains thermal energy. As an illustration, consider two objects attracting each other in space through their gravitational field. The attraction force accelerates the objects and they gain some speed toward each other, converting the potential energy into kinetic energy. When either the particles 1. Pass through each other without interaction or 2. Elastically repel during the collision, the gained kinetic energy starts to revert into potential form, driving the collided particles apart. The decelerating particles will return to the initial distance and beyond into infinity or stop and repeat the collision. This shows that the system, which loses no energy, does not combine into a solid object, parts of which oscillate at short distances. Therefore, in order to bind the particles, the kinetic energy gained due to the attraction must be dissipated. Complex objects in collision ordinarily undergo an elastic collision, transforming some kinetic energy into internal energy. which is further radiated in the form of photons, the light and heat. Once the energy to escape the gravity is dissipated in the collision, the parts will oscillate at closer, possibly atomic, distance, thus looking like one solid object. This lost energy, necessary to overcome the potential barrier in order to separate the objects, is the binding energy. If this binding energy were retained in the system as heat, its mass would not decrease. However, binding energy loss from the system would itself have mass, and directly represents the mass deficit of the cold, bound system. Closely analogous considerations apply in chemical and nuclear considerations. Exothermic chemical reactions in closed systems do not change mass, but become less massive once the heat of reaction is removed, though this mass change is much too small to measure with standard equipment. In nuclear reactions, however, the fraction of mass that may be removed as light or heat, i.e., binding energy, is often a much larger fraction of the system mass. It may thus be measured directly as a mass difference between rest masses of reactants and products. This is because nuclear forces are comparatively stronger than the Coulombic forces associated with the interactions between electrons and protons that generate heat in chemistry. Mass change in bound systems, particularly atomic nuclei, has also been termed mass defect, mass deficit, or mass packing fraction. The difference between the unbound system calculated mass and experimentally measured mass of nucleus is denoted as delta M. It can be calculated as follows. Mass change equals minus, i.e., minus after nuclear reactions that result in an excited nucleus. The energy that must be radiated or otherwise removed as binding energy for a single nucleus to produce the unexcited state may be in any of several forms. This may be electromagnetic waves, such as gamma radiation, the kinetic energy of an ejected particle, such as an electron, in internal conversion decay, or partly as the rest mass of one or more emitted particles, such as the particles of beta decay. No mass deficit can in theory appear until this radiation or this energy has been emitted, and is no longer part of the system. When nucleons bind together to form a nucleus, they must lose a small amount of mass, i.e., there is a change in mass, in order to stay bound. This mass change must be released as various types of photon or other particle energy as above, according to the relation E equals mc2. Thus, after binding energy has been removed, binding energy equals mass change times C2. This energy is a measure of the forces that hold the nucleons together, and it represents energy that must be supplied again from the environment. If the nucleus were to be broken up into individual nucleons, the energy given off during either nuclear fusion or nuclear fission is the difference between the binding energies of the fuel, i.e., the initial nuclide, and the fission or fusion products. In practice, this energy may also be calculated from the substantial mass differences between the fuel and products, which uses previous measurement of the atomic masses of known nuclides, which always have the same mass for each species. This mass difference appears once evolved heat and radiation have been removed, which is a given requirement for measuring the masses of the nuclides involved in such calculations.